Hi everyone, my name is Brock Cooper. This is my final year thesis findings for my project topic to design, benchmark and determine the performance of a low-cost 3D printed 6 degree of freedom robotic arm. Robots are a rapidly expanding field and are being used for a wide range of applications from remote exploration, agriculture, search and rescue, assembly lines and many more applications. My research involved understanding the robot operating system known as ROS and integrate low-cost hardware with the ability of having advanced motion control with a closed-loop system. The key area for analysis in the research is to design and benchmark a low-cost robotic arm. Through researching into the international standards of manipulating industrial robots, performance criteria and related test methods, there are 14 characteristic tests. The purpose of this research was to determine and apply a methodology for a low-cost DIY robotic arm to understand the pose repeatability. What is ROS and why is it used? ROS is an open-source, Unix-based robot operating system which is a flexible framework that has been developed to provide a seamless structured communication layer for communication from off-board to on-board machines. ROS is built using a variety of libraries and functions from open-source projects such as simulators, drivers, navigation systems, vision algorithms, and many more. The software has been developed for multilingual use, being able to write functions and definitions in a variety of different programming languages such as C++, Python, Octave, and Lisp. ROS allows for peer-to-peer communication. What is that, you may ask? This allows for a system of slave devices to receive data from off-board machines that have greater processing power that can process data such as images, point cloud maps, or speech recognition. The project was broken down into 3 key aspects that were crucial for the success of the research, being hardware design, software implementation, testing and benchmarking methodology. The realization of the project came from an existing arm provided by my supervisor. After analyzing the arm, a new design was inspired. Improvements consisted of adding 2 extra joints to have full control over XYZ position whilst being able to satisfy roll, pitch and yaw of the end effector. Another improvement was ensuring all joints have an encoder for closed-loop position control. Lastly, Hall effect sensors were used for homing the arm. The overall design of the arm was constrained to have similar appearance to existing industrial robots. The control box was designed for dual-purpose use to enclose the electronics whilst also acting as an anchor point for the arm to attach to. The main software that was used is ROS, with the custom control packages being written in Python and C++ with a custom ROS launch file. The testing and benchmarking was conducted by planning paths using the Move It Commander Python interface and measuring the readings of the end effector position by probing a dial indicator. Here can be seen the wiring diagram for the control box, which consisted of 3 LM298N motor drivers that were connected to an Arduino Atmega 2560, with the addition of 6 Hall effect sensors all connected using an Arduino terminal block shield. All of the electrical components were powered from a standard 500-watt computer power supply. Why was the project important and the motivating factor behind the research, you might ask? The main reasoning behind the project was to design a simple yet functional 6-axis robotic arm that was cost-effective and required very little hardware and having a sophisticated control interface. The research also included looking into existing robot arms and analyzing the complexity of the designs which required various types of hardware, making them more costly. The existing designs consisted of 2 different types of joint configurations. The first common design used a planetary gearbox that added more weight to the arm and increased the cost of the design, whereas the other configuration used timing belts with stepper motors to control the joint actuation. Both designs required a longer assembly process, making it more time-consuming, whilst also requiring numerous pieces of hardware. To understand the robot transformations for exporting the Unified Robot Description Format, URDF, a kinematic model was required to determine the transformation of each joint from the base to the end effector. The Denevert-Hartenberg parameters for the robot can be seen in Table 1, where they are the robot transformations for each joint from the base to the tool. To ensure that the work was correct, this was verified with applying forward kinematics to the model to convert joint space into Cartesian space. An inverse model wasn't required as this can have multiple solutions and was handled by the Move It library. Here can be seen the custom ROS control package structure that was integrated with the existing ROS libraries. The nodes are contained in oval shapes, whilst the topics are drawn in rectangles. The BCR1 has a custom node that communicates through the ARM command message, sending commands to the robot, whilst the BCR1 telemetry would post the data from the robot to the ROS interface, updating the simulation environment in real time. These both run through the ROS serial node that allows the Arduino to connect with the ROS environment. So we're going to start off by launching the BCR1 hardware main.launch file. This contains all the launch parameters for the necessary nodes and to initiate the connection with the robot. This also will launch the RViz simulation environment, where you can see the robot state will be loaded in. We'll now initialize power to the motors, and you'll see the robot will go through a homing routine. We'll now head back to VS Code and we'll open the Move Group Python interface. This Python file has been written to be able to control the BCR1 planning group. This is using the MoveItCommander Python API. Robot position definition was written to be able to input X, Y, Z positions along with a X, Y, Z and W quaternion rotation matrix. So here you can see we're going to test the repeatability in the x-axis for demonstration purposes. The robot will traverse down to a alignment position. It will then go into a probe position, back to the alignment position, and then back home. So now if we run this file, we'll be able to see the robot run through its trajectory. So here it's probing the dial indicator. It'll hold this position for 8 seconds for a reading to be taken before returning back to its home position. For demonstration purposes, this was conducted 4 times, but for experimental analysis, this was repeated for 30 cycles. This same method was applied to the Y and Z axis. Going back to the RViz simulation environment, we can now enable approximate inverse kinematics, where we can query a goal state using the end effector ball, where we can drag it around into a certain position and plan and execute. And you'll see the current pose and the target pose and the robot position moving to that position. We can then go back to the arm rest position and plan and execute. We can also constrain the movement to one axis, in this case moving in the Z direction. So we can go down and then we can go back up. A random pose can be also selected. So what we'll do is we go into the goal state and select a random pose and can click plan and execute. The robot will then move to this position. We can then go back to the arm rest position and hit plan and execute. The repeatability of the BCR1 was tested for a single point in each axis, meaning the arm would probe the dial indicator in a parallel motion to the end effector. The results were taken and processed to determine the mean for each axis, where the data can be seen with a deviation from the mean value for the X, Y, and Z axis. This data was then taken and plotted in 3D space, where it could be analyzed in plane form. It was evident that the XY plane has the greatest repeatability, whilst the XZ and YZ plane have more significant variance in the distance from the test mean. To determine the overall repeatability of the arm, the distance formula in a straight line was used to determine the distance from the mean test point. The overall resultant positional error can be seen with the largest deviation being 5.488 millimeters.